Hi and welcome again to these videos on dynamics of structures. In a previous video we have discussed different types of sources of excitations of objects and structures. So as an engineer, when these sources cause excessive vibrations to objects and structures, it is important to think or rethink the design. So in this video we'll be illustrating some of the common problems both in civil and mechanical engineering that can occur when a vibration source causes excessive vibrations. The first example we'll be discussing is pedestrian bridges. The first example of a pedestrian bridge is this footbridge in Derby in Belgium. We have discussed that the main source of excitation for pedestrian bridges is pedestrians walking or running, and you see here that the main frequency of excitation for walking is around 2 Hz and for running can be slightly higher. But there can also be some harmonics, so if you are walking at 2 Hz, there is also the presence of second and third harmonics, which are at 4 and 6 Hz. So mainly the excitation for pedestrian bridges is from 1.5 to 3 Hz, and you have to be careful for harmonics. In the case of the footbridge in Derby, you see here the results of computation of first mode shapes of this bridge, and you see that the first mode is around 2 Hz, and so this is a critical mode which could bring the footbridge in resonance for pedestrians walking. Second example is this footbridge in Poland, where you see that here a finite element computation shows 3 modes in the range of 2 Hz, which can lead to potential resonance. Here is a video example of a footbridge that is set into resonance by exciting it at its natural frequency. So you see that it's quite low frequency, around 2 Hz, and can lead to quite some amplitude of vibration. Another example we discussed in the introduction is the Millennium Bridge in London, which at the opening started swaying, in this case laterally, at a low frequency due to resonance as well. So in summary, problems with pedestrian bridges occur when one of the natural frequencies of the pedestrian bridge matches the frequency of walking pedestrian, which is around 2 Hz. Let's now discuss another case, which is high-rise buildings. The main causes of vibration of high-rise buildings are wind and earthquake. So in this first schematic we see the building is replaced by a mass spring system, which is excited by the ground with an acceleration. This is an example of the frequency spectrum of ground acceleration for an earthquake in the United States, so the Santa Cruz earthquake, and you see that the main frequencies are below 20 Hz with a peak around 5 Hz, so quite low frequencies. For wind excitation, we also have a force due to the wind applied here directly to the mass and not to the ground. So this is a different location of the excitation. And of course the frequency spectrum can be quite different. We saw that for the in a previous video that for the Davenport spectrum we have frequencies in the range of 10⁻⁻1 to 1 or even up to 10 Hz. Now this is an example of a high-rise building in China, where you see that by computer you can compute the mode shapes or even measure them, and so the measurement here, which correspond quite closely to the simulation, shows a lot of modes below 1 Hz, so these are very likely to be excited by an earthquake or wind. This is demonstrating how a high-rise building can sway in the wind quite significantly, and the next video is about earthquake excitation.
At the beginning of the tremors, it sways gently at first, and then gets more and more violent.
The top floor swayed back and forth around 60 centimeters, and this continued for more than 10 minutes. Here is a shot of the Shinjuku high-rise district during the earthquake. The footage here is corrected for the shaking of the camera itself. When the video is played sped up, the significant side-to-side swaying becomes clear. The megaquake caused many buildings to sway for a prolonged length of time, resulting in unexpected damage.
So the main sources of excitation of high-rise buildings are wind and earthquake, which can lead sometimes to collapse of the structure, or in other case just uncomfort of people in the buildings. Another source of discomfort of people in a building can be machine-induced vibrations. So to illustrate the problem of machine-induced vibration, consider, for example, a building where here you have a machine that is rotating and so creating a force which is then transmitted to the floor and the surroundings and in people's apartment. So this is the example, for example, of a washing machine. And if you look at the FFT of a rotating machine, so the Fourier transform of signal, this is, for example, an engine, a car engine. You see that these are characterized by a main excitation due to the main rotation speed, so here at 30 Hertz, but you also see harmonics here, one at 60, and subharmonic at half the frequency. So let's see a few examples. So this is the effect of a washing machine on the surrounding. This is the effect. Here you have an engine inside that rotates. You see here the rotating part, and it creates a resonance of the table here. A next example is to illustrate the rotation due to a tractor engine. And finally, this is the example of the rotor of an helicopter, which will lead the helicopter to resonance and to destruction. So you clearly see now the amplification of the motion due to resonance, which leads to failure of the helicopter. In our modern world, we are surrounded by machines, and these machines can really cause problems of comfort, but they can also lead to excessive vibrations, which are problematic for precision equipment. So this is what we are going to discuss now. So consider a building or a sensitive equipment which is subject to some ground motion. So the ground motion could be, for example, a satellite that is put in a launcher, and the satellite is vibrating and transmitting some motion through the base of the satellite. For example, there is the GSFC standard at NASA for this kind of equipment, where we have here the power spectral density of acceleration that the satellite will be subjected to. So you see that there is a gradual increase from 20 to 50 Hertz, then a plateau of acceleration up to about 800 Hertz, and then a decrease up to 2000. So the general spectrum is between 20 and 2000 Hertz, and you have different levels to which these satellites can be tested. So this is an example of testing of such a satellite on a shaker, where the frequency of excitation is gradually increasing. Another example of ground excitation is the problem of comfort in cars. So this is here a rally car, where you see that people are quite heavily shaken in the car. And a last example is precision equipment. So here you see a microscope, and if you zoom on this region, you really see that the image is vibrating due to some ground motion. So the microscope is attached to the ground, and the ground is vibrating, and it's creating some perturbation to the image. So today we are dealing with precision equipment which requires lower and lower levels of vibrations, but we are also surrounded by many more sources of vibrations, and one of which is traffic-induced vibrations. So vibration caused by traffic, an example is a car or a train, tram that is in the street and that is causing vibrations which are directly transmitted through the ground to surrounding buildings. Another example would be the car being on a bridge, on a flexible, quite flexible structure, and the vibration is transmitted to this flexible structure directly from the car to the bridge. So this is examples of big trucks passing by houses and creating vibrations. And in the second example, we're going to see the measurement of the vibration caused by a train passing on a small bridge and the characterization of this vibration in the frequency domain. So you see the passage of the train and the recording.
So this is the power spectral density of that train traveling over the bridge. What I was kind of pleasantly surprised about is just how broadband that vibration is across really about from 20 hertz all the way through 1,000 hertz. It's pretty steady. But there's definitely a peak at 23 hertz in the y-axis.
Apart from traffic, one of the main sources of vibrations on objects is wind. And we have seen in the dedicated video on flow-induced vibration that one of the phenomena is the so-called vortex-induced vibration. So vortex-induced vibration, I remind you that this is a phenomenon where a force that is perpendicular to the constant wind is produced by the alternating vortices, and so it's in the form of a sinusoidal force with a given frequency. This frequency is given by this expression, so a function of the velocity of the flow, the Strouhal number, and the diameter here for a cylinder. And when this frequency matches the natural frequency of the object, of the cylinder here, you are reaching the critical wind speed, which is given by d over st times Fn. So a few examples of this phenomenon on poles. So this is the example of light, very impressive example of light poles in a highway. This is another light pole in a street, and the example of red lights in the United States. Now, other examples of objects subjected to VIV are chimneys. So this is here the example filmed in 95 of a chimney which is undergoing strong wind and swaying laterally. And this is also an illustrative example of the vortices that can form due to the windshield of a car, or a cabrio car in this case. A quite impressive example of vortex-induced vibrations on a bridge in a construction phase, which you can see can lead to a resonance here of this arch and leading to quite high amplitudes. But vortex-induced vibration can also be used in a positive manner, as illustrated in the following movie. So vortex-induced vibration becomes dangerous when the frequency of the vortices matches the resonant frequency of the structure. In this case, the vibration amplitude can become very large, but is limited by the damping in the system. In the case of instabilities, which we also discussed in the video about flow-induced vibrations, the damping in the system becomes zero or negative, which leads to even greater vibrations. We will now discuss the case of galloping and divergence. We have seen in the dedicated chapter that galloping and divergence can be explained with this very simple model with the following 1 degree of freedom equation of motion, where we see that the damping is variable and changes with the velocity of the fluid. So this can lead to some instability, oscillatory instability, when the damping becomes negative, which means when the pole here crosses the imaginary axis. Another type of instability arrives when the stiffness, which is also affected by the flow, goes to zero, and this is called a diversion, so it is a static instability. Example of galloping is typical in these power lines, where usually due to the cold there is some ice, and this is creating the instability because the section is not symmetric anymore. And an example of diversion is given here, where you see that this is a very low frequency, so static close to static phenomenon, where you have high deflection of the roof here due to the wind, when the wind blows at a certain speed. So divergence is a static instability, while galloping is a dynamic instability. Another example of dynamic instability is flutter, and we will now show a few examples of flutter. To understand single mode flutter, we look at this profile here, which is subjected to a lateral wind in this direction. Now, if the body here starts to change, to oscillate or to move in the y direction, the effective velocity that it will see is given by here this vector, which means that the drag will be in this direction and the lift in this one, so they make an angle with x and y. So the total force in the y direction will be L times cosine of this angle plus d times sine of this angle. This angle, the tangent of this angle, is given by the ratio of the velocity of the body and the velocity of the flow. So it depends on the motion of the body, and so the total force will also depend on the motion of the body. If this body is attached to the ground by a spring and a damper, then the equations of motions are the following, where I remind you that alpha is a function of the velocity. Let's now do a little bit of mathematics. We assume that alpha is small, and we do a first order development of the lift and the drag coefficients, neglect the second order terms, and replace alpha by the ratio of the velocity of the body by the velocity of the flow. This, by putting everything on the left hand side, leads us to this equation of motion. And now we consider the fact that the lift and the drag coefficients are given by this function of the flow speed, where we introduce the coefficients of lift and drag. And so by replacing, we see now that the variable damping is a function of the derivative of the lift coefficient with respect to the angle plus the drag coefficient. Now, for certain profiles, this term can be negative, which leads to the fact that when u increases, the velocity of the flow increases, the damping can become zero and even negative. So this is the phenomenon of single mode flutter, and graphically in the complex made, it means that the pole, the natural frequency of the system, which is initially stable, will gradually drift to the right due to the increase of the flow velocity and leading to some instability. Another type of flutter can happen, which is called coupled mode flutter. We're not going into the quite complex mathematics, but graphically you see here that if you have initially two poles and that when the wind or the flow velocity increases, they tend to come close together, and this one pushes this one to the right and leads to some instability. A very famous example of this couple mode flutter is the Tacoma-Nauros Bridge, which collapsed due to this flutter. Another example of flutter is shown here on an aircraft. So you see that when the aircraft will reach a certain velocity, there is some high vibration that appears at the back of the airplane. I would like to say a word to finish this video about VIV versus instability. So VIV is a phenomenon in which the flow causes a perpendicular force that is harmonic and can lead to the resonance of the body. And this resonance can lead to very high amplitudes, but these amplitudes are always limited by damping. VIV mostly happens for symmetrical objects, whereas the galloping or flutter instabilities happen for sections which are not symmetrical. Nevertheless, of course, instability will lead to high amplitudes of vibration, but we saw in a previous video that these vibrations can be limited by a third order term, and so will lead to limit cycle oscillations. So in theory the amplitude is unlimited, which is why galloping and flutter is much more dangerous and can lead to failure, but in practice it may be difficult to differentiate between these two phenomena, and it's usually calculations which will tell us at which flow velocity VIV or galloping and flutter can occur. Now, whether it is VIV or instability, large amplitudes of vibrations are not good for structure. They can lead to fatigue on the long term or to failure on the short term if amplitudes are really large. This leads us to my summary of this video. So, excitations of objects, structures, are described both in the frequency and the time domain. Knowing these excitations will allow us to do a model, as we have seen in previous chapters. So knowing the mass, damping and stiffness matrices, we can compute the model properties, project in the model basis and do a computation. This computation can be done both in the frequency or in the time domain. And the question then is, are these vibrations level that are computed acceptable or not? If yes, of course, nothing has to be done. But if the answer is no, then we need to redesign our structure or find remedial measures to reach these acceptable level. So this will be the topic of next videos. I think you have understood by now that there are many sources of vibrations and many different phenomena which can lead to excessive and unacceptable vibrations. As an engineer, it is very important to understand these sources and the different phenomena in order to be able to do a proper design of structures.